and welcome to this webinar. We are going to talk about how we can use Copernicus data to assess phenological agriculture events. And with us today, we have three speakers. They will introduce you to phenology. They will talk about the tools that we can use, how to access Copernicus data, and so on, and a little bit more. My name is Bente Yabi. I'm going to be your host today. And before we start the program, we normally warm up with a weather report around the speakers' places. And we also encourage you to tell us what the weather is like where you are living and where you are living, so that you familiarize yourself with the chat box where the Q&A will happen. Well, you can ask questions and comment in the chat box, and we will answer your questions during the webinar. So we start with that so that people can get in the room and be on time for the program. So with that, let's hear what the weather is like where you are, Cozmin. Cozmin, did you hear me? Kindly asking for a weather report.
Yes. Good morning, everybody. Okay. It was morning, everybody. I'm Cozmin. It's the very nice weather. It's sunny, and it's really, really nice spring.
Sounds lovely. How about you, Sophie? Where are you, and what's the weather like?
So good morning, everybody. I'm also in Belgium, center of Belgium, and the weather is also sunny and temperature will be very nice today.
Ah, lovely. And Guido?
Yes, I'm in northern Italy, and the weather is nice and sunny, but at the moment it's quite cold. So, but it's warming up to about 18 degrees today.
Oh my goodness. Yeah, well, I am in the Arctic. I'm close to Buda, so beyond the Arctic Circle. And today we woke up to 15 centimeters of snow. So a little different than the weather where you are. So let us hear what the weather is like where you are. I see that we have somebody, Samantha from Finland, telling us they got even more snow than us, 20 centimeters around 0 degrees. So Europe is very varied in terms of weather today. Now, a little bit about the program. We will start by introducing the concept of phenology in general and also for agriculture, and then you will learn about the challenge that Cozmin is mentoring. So Cozmin will start, and you will learn more about who Cozmin is also when we do a tour de table. Guido is going to be the next one to introduce us to how you can access Copernicus data and some of the tools that you can use to analyze this data. And finally, yet another batch or bucket of tools will be presented to you by Sophie. So you will get a lot of information today, and we hope that you will join us in this hackathon. So this webinar is part of the Dubrovnik INSPIRE hackathon, where we are exploring different ways of using Earth observations, in this case for agriculture, for phenological observations, and always using Copernicus, of course. So yes, we do a tour de table and then we start the program. Again, I would like to remind you that we really want you to ask questions in the chat, and we will answer them the best we can, either in between each of the presentations, but we will have a Q&A at the end of the last presentation, so where we can actually also discuss a little bit. If you have a Chrome browser, you have webcam, headset, a good internet connection, you can raise your hand and we can invite you into the room also. That's an option, but there are some technical requirements. All of you can ask questions and comment in the chat box here. Okay, we do a tour de table. We start with you this time, Guido. Can you tell us a little bit about you?
Yes, I'm Guido Lemoine, sorry. My wife is making some noise in the background. But I work for the European Commission. I mean, now, of course, I'm at home because in northern Italy we are in lockdown. And at the European Commission, I work for the Joint Research Center in a group called Food Security. So dealing mostly with agriculture in Europe and also, say, at the global scale. And my role is really to introduce the Copernicus data in this work. So we are doing high resolution assessments now, where we did lower resolution assessments before. And of course, there's a lot of big data analysis involved there. So I'm also working on the IT tools that we need to help integrate this data.
Excellent. And Sophie?
So, yeah, I'm Sophie Bontemps. Good morning, everybody, once again. I'm working in the Université Catholique of Louvain in Belgium as a researcher and also project manager. And I'm mostly involved since now 5-7 years in a research project funded by the European Space Agency. And these projects really aim at pushing the use of Sentinel data in agriculture applications. And so I will present you some tools that we have developed. And so they're agriculture in general, but also very focused for phenology.
Excellent. And Cozmin, tell us about you.
Yeah. Good morning, everybody. Once again, I'm Cozmin Lucau. I'm from Belgium. I'm working in the Wallonia Agricultural Research Center, dealing with topics using Sentinel satellite data on agricultural application. We are trying to do the link to close the gaps between farmers and research and administration. And I will present you very shortly this phenological challenge just after that.
Yes, exactly. And I hope that your internet connection will be more tolerant to your voice rather than the video, because they were breaking up a little bit. But I think that will be better when we are now turning into your presentation, Cozmin. So I think we can, we will disappear our, we will not disappear. Our videos, we will turn off our videos or our cameras, and we will listen to Cozmin.
Thank you, Bente. Yeah, I don't know, can you
You're
see
all
my
set.
screen?
Yeah, you're all set. Go ahead.
Okay. I very shortly present to introduce you this topic from today webinar concerning assessing of phenological events in agriculture based on Copernicus data. It's a presentation made by me and my colleague Yannick Cornell, which is the expert on this field. And the overview of my presentation, I will shortly just give you the definition of phenology, some application in agriculture, and for sure the link with Copernicus data. Now I start with assessing phenological definition of phenology. That basically is the study of periodic plant and animal life cycle events and how these are influenced by seasonal and interannual variation in climate, as well as habitat factors such as elevation. It's a definition from Wikipedia. You can find here a more complex definition, or more scientific if you want, just as example. And to know that this term was first introduced in 1849 by the Belgian botanist Charles François. And it was a definition a little bit more short, but it's more the same meaning. To give you some example to better understand this phenology topic, it's about the emergence of leaves, the first flight of butterflies, the first appearance of migratory birds, and the date, for example, of leaf coloring and fall in deciduous trees. Two more examples from historical phenological events. One is concerning French records of grape harvest dates in Burgundy. They used this long series of record to reconstruct spring-summer temperature from 1370 to 2003, and we have here the graphs with the temperature evolution. And another one, it's interesting. It's about cherry boom in Japan, when the full blossom date for Kyoto's cherry trees can predict March temperature to within 0.1 degrees. It's really impressive, this study, and it was start very long time before Copernicus. That's we discuss about Copernicus today, not with this one, but about European system. Now, other examples, it's the assessment of the vulnerability of species, population, and ecological community to ongoing climate change. In the left part, you can see the climate change in the WAC living dates, and in the right part, you can see also the same impact of climate change on the flowering date for winter wheat. It's about prediction of human health-related events such as allergies and mosquito season, and we can see that now we are at the beginning of the spring with this period when the pollen and even fungal spores can give you some allergies if you are sensitive to that. It's also about management of invasive species and forest pests. You can help management of the forest, having a prediction of insect wildlife stage. And for sure, it's important also by helping us to understand the timing of ecosystem process, such as carbon cycling. I mean, you know that the length of growing season at the ecosystem level have a consequence for carbon cycling. In agriculture, the phenology can help us to optimize when to plant, to fertilize, and to apply treatments. In the left part of this slide, you can see the crop growing season with different phenological stages of the cereals and the quantity of nitrogen to be used at field level. And in the right part, it's a very nice example with potato fields. There are two fields near one of the other one, and there are really different phenological stage. One is it's green, and the other one it's already and at the end of the season. And this information is also useful for to plan the harvest operation of a territory, because the farmers or the industry will like to know which is the homogeneous territory when the crops are ready to be harvested. Another example with the fields of the potatoes here. And for sure, the phenology is important and can help us to estimate yields and forecast yields provided by the crop growth monitoring systems. And you can see a scheme with different phenological stages and the crop growing season for the same for the cereals. But the links with the Copernicus data. We know that different remote sensed indicators for assessing vegetation phenology, it's based especially on the NDVI or LEI indices, have already been proposed in various studies. These agrophenological indicators are computed on moving average, thresholds, logistic curves, maximum rate of changes, and different methods, but it's not really the moment to go more in depth with this topic. Just to know that the majority of that are based on optical data, and it's really okay that when we have the optical data, it's called Sentinel-2, available. We can see, for example, here in this graph, the temporal evolution of NDVI for 3 different crops: winter wheat, corn, and rapeseed. and it's okay. When we have the data, there are no problem. But the problem could happens when there are no optical data. Another example here for a winter wheat field, when we can see that during more than 1 month we don't have any acquisition, and mostly due to the cloud cover. And what we can do in this situation, one of solution could be the use of Sentinel-1 SAR data, which is the active sensor, and it's weather and daylight independent. Just to show you an example of optical data from Sentinel, we can have this classical image or this NDVI, the vegetation index calculated from the Sentinel-2 data, or this Sentinel-1 radar data. You can see the differences. It's so important, at least visually, but not just visually. We can say this backscatter coefficient images and also the coherence product. I don't enter into details, just to visually know about these differences on the quality and the quantity of information in one case with optical data and using this SAR data. And now we are going more and more in this combination of all this data. From optical, when we have it, we are very happy, we are using that. But when we don't have optical data, we use also Sentinel-1 radar data as coherence product or backscattering coefficient product, and for sure we use meteo information. Knowing that this Sentinel-1 radar data products are used, but we have to adapt it with new algorithms or to adapt some models or to find new models. For example, here we just mentioned the water cloud model. It's a model used for the estimation of LEI, for example, from SAR data. And it's just an example. We can go more in detail with different questions about. And just to conclude about this challenge, we have the Copernicus data, we have Sentinel-2. That's data that are often used to estimate phenological events. But the idea is to use Sentinel-1 SAR data and maybe Sentinel-3 data to adapt or to find new algorithms or model using high power computing system as DIAS or Google or Amazon or cloud computing system. I think Guido present you more in detail this part. And for sure, the use of complementary data, meteo, ground truth data, and yeah. Thank you for your attention, and you can find here my email address if you have different question, comments, or remarks. Thank you very much.
Thank you so much, Cozmin. We will also provide, or you will provide your email address in the chat box so that people can reach you there. Otherwise, I have also provided a link to where you can register for the hackathon, and we really recommend that you do that if you're interested in working on these challenges here, working with this Copernicus data for assessing the phenological stages in agriculture. So we will repeat all this to the end as well. So this webinar is actually, just to mention that this is the second time we run this webinar, and it's part of the challenge of the Dubrovnik INSPIRE hackathon. I think, and it's an EO for Agri. So it's an EO for Agri. It's a Horizon 2020 project, which is collecting information about the needs of agriculture for Copernicus data to develop further the Copernicus services in the future. That's one of the goals of EO for Agri. So just to give you a little bit of context. And one of our partners in EO for Agri is actually one of the DSs, Mundi. So there's a possibility to work with us on that. Now, Guido, let's talk more about the Copernicus data itself and what tools that you can offer to those who are participating. Are you there, Guido?
Yes, I'm here. I'm here.
Yeah.
I was just trying to figure out again how I do the screen share, and it should be like this. Do you see this?
Yes, we do. We see your screen.
Okay, I'll start at the beginning, and I'll do in present mode. So, yes, so I will follow up on Cozmin's part, more with the sort of technical details on where all this data is. And of course, here we talk about the Earth observation part, and I'll give you some hints on where to find the data, and also, of course, how we process that data into information on phenology. So I don't need to repeat what Cozmin said about phenology. Maybe interesting here is that, of course, we are in agriculture. We are not, say, interested so much in when the oaks are getting leaves, but more into the things that are related to agricultural production. And but in the definition, you have these two factors: life cycle events and habitat factors. And I think what is very important, of course, in agriculture is that to some extent, farmers can, manipulate these habitat factors, because they can, of course, manage, for instance, water supply, but also fertilizers, the way they plan their management activities. And that is, of course, also important information that you can try to derive from Earth observation. So it's not just about seeing the plant grow, but also maybe looking at specific events that relate to phenology. And of course, you can think about harvesting as well, but also soil management, plowing fields, keeping catch crops on those, etc. So all sorts of things that, if you think about agricultural management, you can try to translate into the way you can see this in imagery. So that is really the trick, right? So you have to first understand what these farmers are actually doing, and not necessarily an individual one, but of course groups of farmers that typically time their activities according to the seasonal events, etc. But and then, of course, you need to understand how that translates into the information that you find in Sentinel-2 imagery, Sentinel-1 imagery, very high resolution imagery, whatever you have available. And then, of course, here we are focusing on the Copernicus data, but you can imagine that there are many other sources of information that you can try to integrate. Not just in fact, of course, not just Earth observation data, but you typically need this information about local management practices, crop types, all the sorts of things that you can already sort of use to do your estimation. And here we focus on the data assess. So important for you to know, if you don't know that yet, is that this Copernicus program produces, so it's the European Union's Earth observation program, and it produces, it has actually launched a number of sensors, some of which are at high resolution, and that's Sentinel-1 and Sentinel-2. Sentinel-2 is like Landsat, if you know that. So it's a multispectral instrument that registers in the optical and infrared domains. And the Sentinel-1 is a SAR, so that's quite specific. Not many people use SAR, but increasingly people use SAR now over, for instance, for agricultural information. And both of them have a 10-meter resolution. And that's interesting because you can then look at individual fields, parcels that, of course, have a particular crop, have a particular management, etc. So And what is important is that the data is available full, free, and open. So you can just go somewhere, find the data, and download it if you need it. But of course, downloading is not always the best solution, but we'll come to that in the next slide. So the key sort of entry point here is this link here, which I would suggest you should try out. And this is the ESA access point. So ESA is the organization, the European Space Agency is the organization that manages, say, the technical components of the Copernicus program. So they launch the sensors, they manage the data, and they also keep this access point where you can get the last year of data. So if you want Sentinel-1 or Sentinel-2 or Sentinel-3 or Sentinel whatever, there you can go here and find that data. And it is free of charge, but you do have to have a registration there. But that's quite simple. You just register with your email, and that's it. And I'll just show you the interface there. So that's typical map interface where you can define your area of interest, which is in this case this orange yellowish area, and then with a few parameters like the time window, maybe the type of sensor that you're interested in, you can get a whole list of images that are available for that period. Important for you to know is that Sentinel-2 comes over every 5 days, and Sentinel-1 comes over every 6 days. But Sentinel-1 is also doing orbits, like ascending and descending. So in principle, you have lots of data available at this regular interval. And you see that on the left side, there is this list of what they call products. So these are these blocks, and you can you have a link there that you can just click and then download the data. So the data there is organized in blocks, which is you understand that the sensor basically takes a whole strip of data, but in order to manage the volume of these data sets, they are cut up in blocks, which are between what is stated here, between half and half a gigabyte to 8 gigabytes. So they're quite big, but so if you have a, of course, if you have an internet connection that is not so say powerful, then you have a hard time trying to download all this data. And then the point is that in some cases you still have to do some processing. So it's not that if you have downloaded it, it fits in your GIS, and so you have to do some extra work. And that means that you have to start really thinking about, should you download all this data? Should you really not try to find a solution where the data is actually already processed for you? And for visualization, there are these two links here that you can again you can look into. I'm not going to go there now, but these are nicer visualization options where you can just look at an arbitrary area and understand what is available, and how to get that data through those particular interfaces. This is what you try to aim at. So you want to have you have an area, and for instance, in this case, I have all the outlines here, which is a bit specific to the European situation. But imagine that you have this yourself. Then you can match that with your imagery. This is a Sentinel-2 image, where you can you can see all the variation in the fields, between fields, but even within a particular parcel, you can see subdivisions. You can see the forest parts, of course, the infrastructure. So this information, imagine that you have this every 5 days, will give you all lots of information on the progress of the agricultural fields. And that's interesting because, of course, what is very nice about Sentinel-1 and 2 is that this frequency, this frequent updates, is matching very nicely with the information that you would like to have at a parcel level. So this is an example where we, in this case, we are using the cloud compute solution that is called DIAS. I'll go into detail in a few slides, but basically it allows you to assess any area, and then for this area you can then without knowing all the complexity of how things are divided into blocks, etc., you can then get the image fragment that is relevant for your particular position. In this case, we're looking at a particular parcel, and what is nice here is that we are trying to see what happens to this parcel over time. And so you can look in the time dimension in this top right graph, and you see how it varies over time. This is NDVI, so this is something that relates to the green vegetation cover, so whether something is green or say bare. And what is interesting here, that in the end you see that it drops several times, and that relates to the fact that this is an alfalfa field which is in Spain, and it is mown every in summertime. It's mown almost every month, about 5 to 6 weeks, and of course this gives you an idea on active management, but also of course you can translate some of these say quantitative effects into how much was grown here and how much was harvested. Now in Spain, of course, you're lucky because you have nice weather in the summer. This is, of course, is an irrigated field, so it has a very clear response. And but of course, in many cases, you have cloud cover issue. So you see that in spring and in winter there are some gaps in the time series, because in those parts of the month we're not able to get a cloud-free image. That's why we're also using Sentinel-1. So Sentinel-1 is a radar, and it has no problems with clouds. That is the first important thing. So if it acquires an image, you will have it. It has there is no issue with gaps in the data, masking, etc. So that is very useful. It's also a calibrated instrument, so you get directly, you have say quantitative information from the areas that you look at. You can do these kind of compositions. So for instance, here you see this is the Netherlands, and that there are no lines anymore that relate to how the data was say set up in blocks, etc. So that is very useful, because there are two things that relates to this. You have many acquisitions. So in fact, in the left map, you can see how many times the instrument is recording, and in most of the EU, you have at least 2 to 3 acquisitions per week, and that's very nice, because again, this relates very nicely to what we are interested in. And of course, it's also already available since 2014, 2015. So already now we have several years where you have continuous data, and data is of course consistent over time, and that's a very important aspect as well. And what is also nice is that if you have a regular time series that is consistent, you can stuff it into machine learning and do quite nice things with all the modern deep learning, convolutional networks, etc., that are available in software. This is just an example, and Cozmin already showed it, that you need to, this is not an NDVI profile, but something that is derived from Sentinel-1, the backscatter coefficient and the coherence. And in the same way as you have NDVI information in optical, the radar gives you information on the crop cover as well. So for instance, here you see from May on, you see a crop growing. It goes up, and it has a similar kind of behavior as NDVI. This is a sugar beet, so it rapidly becomes from bare soil to green, and that's what you see here. But what is also interesting, maybe in this case, is that before there is a crop, you can also look at what happens to the fields in terms of soil preparation. So in this case, there's a winter period where the field remains a bare soil, which is rough, like a plowed field. Then suddenly in early spring, in April, it is converted into a seed bed. So it is a flat field, and you can see that in the radar, that difference. And then, of course, as soon as the plant emerges, you have this green up that is also registered by the radar. And in that case, it's important that you are aware of what kind of weather was there. So because also for radar, the soil moisture, but also freezing, snow events are important to understand. So you need to be able to interpret the information with ancillary data. Okay, so you've seen that now already, that it's the data is really multi-dimensional. You have a space dimension. It's available basically everywhere, so you don't have to limit yourself anymore to a small area that you are familiar with. You can easily do a whole country. And temporal, because you can get all the data for whole the year. So for radar, for instance, Sentinel-1, you can get up to sometimes 200 observations per year that you can combine in a time series. Of course, also with Sentinel-2, it's every 5 days, so 72, 73 observations per year. And you can, of course, apply this either in agriculture or in forestry or in water, all the thematic domains that you may be interested in. And you typically want to, you don't want to restrict yourself to particular settings. You want to be able to get this data wherever, whenever, and at the scale that you need. So, and that then, if you reflect back on this problem of the size of the images, you should then go away from the idea to go download all the data, because soon your system will be filled up, and you don't even know anymore where the data is located on your own system. So that's where the cloud computing comes in. So these are solutions that are not only providing you with cloud compute power, but also access to this full archive. And that's very important, because the idea is then that you're not going to get the data and download, but you get the data, you process what you need, and you actually maybe download only the result. But of course, you could also think that you could keep that result on the cloud computing instances and then serve it through some web solution, whatever. So the cloud environment gives you this full environment, which allows you to assess and compute with the data. And that's very important, because there is no limit in the complexity that you can then integrate in that processing. So you can, of course, do a simple visualization, like I did with these chips. I make a band combination, and then I do a bit of a stretch, and that's it. But that's very simple. But you can do segmentation, you can do classification, you can do machine learning, you can do all the sort of, say, higher level things that you would like to apply to this data. Now, I'm not sure if you're familiar with the solutions there, but there's Google Earth Engine, and that's has been around for about 10 years now already. And it is, in a way, it's a standard, so it allows you to do a lot of sophisticated work with not just Sentinel data, but many other data sets as well. And in a way, it is also a very smart cloud-based solution. In Europe, we are now, under the Copernicus program, we have what is called DIAS, which is the Data Information and Access Systems. And there are several of those, and they are these cloud solutions that offer cloud computing with direct access to the full archive. And that's what we want. And also now Amazon is doing this, but only for Sentinel-2, for instance. I've heard that Microsoft is starting to do something. IBM has always said they would do it, but they never did. But okay, so there are many technical solutions that are now trying to aim at this cloud compute domain, and it has become really the essential tool that you would need. This is, for instance, how we work on the Copernicus DIAS. Typical for a cloud solution, you have access to a machine. With that machine, you can create new machines. You set up all the tools you need, the database. You have then direct access to what is called the object store, where all the data is. And then you can launch as many machines as you need. Of course, how much, depending a bit on how much credits you have. Because with those, say, additional machines, you can now do work in parallel. And that's, of course, very important, that if you have a nice algorithm and it works nicely on a small part of the image, then you want to do this in parallel to be able to do like a country or an arbitrary area that you want. What we are using on the DIAS is only open source. So all these solutions, applying advanced algorithms, etc., you can actually do with open solutions. In fact, I know of, I don't have actually knowledge of systems that are not using open source in that case. So again, open source here is the default, and it's up to you to put these elements together to do what you want to do. For instance, here in this case, we are using Docker for parallelization. You know, the GDAL maybe. The GDAL is for geospatial data assets. Python is an essential part there in the Python tools. Then you have web server parts and of course the database. And in the case of the database, we're using Postgres, and there's many machine learning libraries now available as well. This is, I think, my last slide, because I'm thinking I'm running out of time as well. But if you look at all this complexity, we have phenology, we have Earth observation data, we have geospatial data in the form of vectors or OpenStreetMap road maps, whatever kind of diverse data. You need to be able to combine that information to and agronomic knowledge, of course. So you need to be able to combine it. So, and that means, and I think that's interesting in the context of this hackathon as well, you need to find those, it's very difficult to find all the expertise in one person. So it's almost, obligatory to look at these issues in a kind of a team setup. And then you want to know, be sure that you have the right expertise in your team. So what kind of knowledge would you need? This is, of course, directly related to agriculture. You need to understand how crops look like, how they grow, what are the typical practices related to these crops. And then the second one is, of course, you need to understand the physics. So what does this mean in terms of things I can see in Earth observation? So for optical, this is not so difficult, because you can reason like, okay, if I see green in a optical combination that is natural colors, then of course it relates to a green cover that you also see in the field when you go there on your bike. And but it becomes a bit more complex, of course, if you start to think about infrared, shortwave infrared, and then of course if you think about radar, it becomes even a bit more complex. But so that's important to understand. What does it mean if something changes in the field? How does the system understand that? And that, of course, includes also the other factors that are not related only to the crop, but also to the soil, the water management, the weather conditions, temperature, etc. Then you need to understand how these cloud solutions work. So programming is important, and as I said before, most of this is running on open source. So Linux, Python. That's you want somebody who knows databases, etc. So that's another part of the picture. Then, of course, in a situation where you would like to apply this, you need to understand where the reference data comes from. Where are there digital vectors available? Is there a parcel registry? How do I get maybe some ground data? So should I go around and do a survey to see what is the current state, what is the next state, etc. Topography, hydrology are important events as well. For instance, are the crops irrigated or not? Because that then that cancels some of the weather parameters that you that may be having an influence, etc. So all this information is important. Statistics, of course, and then of course the real question is whatever I see here with phenology, and is the season normal or not normal? But what is important then? How does that link to yield and production? It's not sufficient to say, oh, I know where this crop is. You need to know what is the total area of that crop. You need to know what are the conditions of that crop in a statistical manner. So not like one crop or some crops, but all crops. And then you need to try to translate this into how much is being harvested, how much maybe become available on the market, or in the local market, etc. So these are all, say, then questions that are more economic, if you want. But it's really important that, of course, you start with a very that the most accurate product that you can derive, or the most accurate information that you could derive from Earth observation. Okay. Okay. This is just one other thing that we're doing. Of course, this is all about digital technology, and the idea is that you need to capture this information in a smart way, in a fast way, in a cheap way. So here we are experimenting with roof cameras. So we put cameras on top of the car, drive around, and then try to apply computer vision to figure out what crop is being grown along the road, and of course what stage it in. So this is work in progress, but it's just one part of the overall picture. Is that it's not about only Earth observation. You need to also be able to think about other ways to integrate information that helps you derive more value from the Earth observation. Okay, here are some references that you can look at, which go a bit more into detail on what we are doing, and we'll give you some hints as well. But of course, there's lots of literature. Fortunately, now most of the literature is becoming open access. So again, that's nice. If you have open data, open source software, open access results that you can quickly reproduce, then we're learning much faster in these days than what used to be the case. Fine. So that I'll leave it at that. And if you have any questions, then please go ahead.
Thank you so much. Thank you so much, Guido. Absolutely, very comprehensive, useful set of information there. We have had a few questions, but I think we need to move to Sophie. But I would like to just answer some of them, and then we will come back to the questions. Thank you so much for them. Questions and comments, we will come back to them in the Q&A. Now, we have Afis Ali Imran, who's asking, can we get free data or products from Diaz or Amazon? As Guido has said, the data is free. It's the processing that, and using cloud for that is not obviously free, but we will have some capacity to that's free for this hackathon. This is correct, right, Guido?
Yes, I mean the data is free at this point. When I said the ESA access point, there you can get the data and download it as you want. Also, the DIASs are making the data available for free. The same data that they actually harvest from this ESA access point. In Amazon, I'm not so sure, but I think you need at least an account there, and then somehow I think they will charge what they call egress. So that means that if you download data, it will be charged a few cents to your account. But Google Earth Engine has also an account model, but it's free, so you can sign up for free accounts, and then through that interface, there's also a possibility to download data for free. But again, think about it. Do you really want to download data? That's not really, I mean, it's an option, of course, but it's if you want to try some data, sure. But I mean, if you really want to do serious processing, then it is better to actually move on to these platforms. I have another question here about BBCH that I mentioned. In fact, I don't know where exactly it was in my slides, but in fact, yeah, this is a formal coding of crop phenology stages. So for each crop, you have particular codes that say, if it's code say 31, it means it is when the flowering starts, and so there is there is a website or there's a Wikipedia page that explains what is BBCA.
Yeah.
Yeah.
So Shadrach is asking if the Sentinel data is covering the entire world. We have a lot of attendees from all over the planet here, so they are obviously interested to learn if Sentinel or the Copernicus data covered the world, and yes, they do. So and Guido, like you said, the data is actually free. It's just different ways of accessing the data that might be well, some are charging, as you say, maybe the Amazon, but this is one of the advantages of becoming a participant in this hackathon, that you learn how to get access to these data for free.
Yes.
Yes. So we will turn back to the Q&A afterwards. Now I think we are ready for you, Sophie, to make sure that people who are only set aside 1 hour, we didn't say how long this would last. I am willing and able to continue also a little bit over the hour, so that we can allow some discussions and kickstart perhaps the work in the hackathon. Okay, Sophie, you are ready to go?
Yes, I am. Do you see my slides?
Absolutely.
All right. So I think that the presentation before already made the point that Sentinels data are really a game changer in agriculture. And this is for varying reasons. I will not repeat, but maybe one thing that has not been mentioned really clearly up to now is that Sentinel data is a game changer also because this is a long-term effort from the European Commission. So this is not that you get your Sentinel-1 or Sentinel-2 data today all over the world, but this is also that you will get this data within 5 years from now, and within 10 years and 20 years. So these data are there, they are secured, the budget is there, they are free and open data, as Guido mentioned, and so it means that you can really start thinking into operational applications. And so this is really something new in agriculture that was not really possible before, and that opens a lot of new possibilities. So of course, the amount of data that you have to handle is huge. You can see here the amount of data which is acquired every day by Sentinel-1 is more than 4 terabytes, and this is more than 1.7 terabytes for Sentinel-2. So you need to get the right environment, ICT environment, to use these data, but these data are there and they are wonderful. So this is really something new. Of course, for agriculture, what is really important is also the specifications of these data. For Sentinel-2, what is key is really the 10-meter resolution. So between 30 meters and 10 meters, you can see here that there is a big difference, and the big difference is that you can watch at your field. So this is something completely new with open and free data. You can see your field, and so you can do your monitoring at the field level, which is really important for phenology. Of course, as Guido mentioned, with Sentinel-2, this is optical data, so you always have the cloud cover problem, but you can nicely complement it with Sentinel-1, where Sentinel-1, you have very dense acquisition time series, and each acquisition can be used. So from the time series analysis, you can really pick up the dates of the events you want to monitor. So here you have the revisit time of Sentinel-1, Sentinel-2. So this is over Europe, but so the nominal specification, so is for Sentinel-1 every 6 days plus the overlapping of the orbits, and with Sentinel-2 every 5 days. But in Europe we are lucky, we can get much more data thanks to the overlap of the orbits. So this is really something which is wonderful in agriculture, and the situation in agriculture is that this is not really not only an evolution, but also a kind of revolution in the applications that we can develop. So we spend some time on the data. Guido mentioned that we have also more and more possibilities to access the data with the clouds. And we have also more and more possibilities with tools that are there to process this data and to process them at a basic level. And this basic level, these basic products, can later be used by scientists and other developers to develop most added value products, most added value applications. And so I will spend some time here on this concept of existing tools to process basic products for agriculture. And I will present you the Sentinel-2 for agriculture system. This is, I mentioned at the beginning when I introduced myself that I have been working in different projects for the European Space Agencies, developing tools. This is one of these projects. So the Sentinel-2 is open source. So this is a system that really starts from the beginning. So downloading or reading, if you are working on a cloud, the level 1 of Sentinel-2, possibly also Landsat 8, and that will ingest and process in a seamless way these Sentinel-2 data into 4 types of products that you can see here on the right. So the first one is a cloud-free surface reflectance composite every month at 10 or 20 meters, depending on, of course, depending on the band of Sentinel-2. Then you get also cropland mask. So for each pixel, so at 10 meter, you get the information if your pixel is cropland or not. And this product is updated every month during the season. The crop type map, this is also a map at 10 meter resolution, so by pixel, which gives you the main crop types. And you get vegetation status indicators, so NDVI, LAI, F-cover, FAPAR, that I produced every week or for each acquisition of Sentinel-2, and which is delivered at 10 meters. So this is the system. The system, I mentioned that it starts from the level 1C Sentinel-2 data, and so it includes a module to make atmospheric correction. This module is the one developed by the CNES in France, which is named Maya, and which is a bit different of the one which is used currently by the Copernicus service, so which is the Sentinel-2 core. But it means that you have the possibility to run this Maya atmospheric correction. We think that the cloud detection with this Maya is better. This is why we implemented it, but it takes time and resources to make this processing. So there is also the option to directly read the level 2 data that are available on the different websites or on the different clouds. So this module of atmospheric correction is really an option. So this Sentinel-2 system, this is it has been developed during a project which lasted 3 years. During the first part of the project, this was really the implementation and development of this tool. And during the second part of this project, this was the demonstration. It means that the tool I have presented has been tested and demonstrated at national scale with 3 current countries. And when I say with, it means that this is not us who did the demonstration. We did it really with national partners in Ukraine, South Africa, and Mali. And so this was made at national scale for these 3 countries. And we also worked over local sites all over the world. So you can find more information about this system on the website that here is mentioned on the slide. So how does it work? This toolbox. So before the monitoring period, you have to parameterize this system. So you have to define your area of interest. You upload a shapefile with your polygon. You have to define the period of the monitoring, so the period in which you are interested to get the products. The crop mask and the cropland, you will be asked during the season to upload also some in situ data, field data. It means a shapefile with polygons, and for each polygons, you say if this is a cropland or not, and if this is a cropland, you give the crop type. So this is information that will be needed by the classification algorithm to make the output. And that's it. This is a system, maybe I forgot to mention on the previous slide. So this is a system that can be run on the cloud or on the local server with the advantages and that were mentioned before by Guido for both options. And this is a system that can be used in near real time or offline if you want to reprocess past data. But in near real time, it means that if you want to make really an operational application in phenology, you are interested in getting your LAI along the season, this is really fully possible. So before the season, you parameterize your system, and as soon as the season will start, the system will check on the data provider if there is a new Sentinel-2 acquisition which is there. And if this is the case, it will automatically process and deliver to you the LAI. And so along the season, during the season, you get your data which become available at the user interface of the system. And I will not redo the animation, but this is the same for the other products, the cropland and crop type map. From the middle of the season, you will get a cropland mask, which is updated every month, and you will get 2 crop type map at the middle and at the end of the season. So this is a bit the idea, the concept behind this Sen2Agri system. This is open source. It means that it's building on our existing software. You can see here the main one. And I really insist on the fact that this is a tool that is not only R&D tool. This is something that has been demonstrated. You can see here, if we look at the application readiness level milestone from the NASA, we are really close to the top. What does it mean? It means that this is a tool that has been developed by us, tested by us, demonstrated by us, but also tested by external users and used operationally by users which are not from the developers. So it gives you a level of confidence in the tool. So for instance, this Sen2Agri tool is used by the World Food Programme to monitor the growing of the vegetation in the cropland of countries which are at risk for food insecurity. And so they combine this Sentinel-2 information with other alert system, to really be informed in near real time if the vegetation, if the crops are not growing as expected, and so they can alert of a possible problem. So this is really to confirm the fact that this is operational. So coming back to my revolution in agriculture, so we have the data, we have the infrastructure, and we start having basic tools that will provide to any users basic products on which they can build to make more advanced research. Another aspect that was briefly mentioned by Guido, and I will not spend much time on that neither, because we do not have the time. This is the data is very important, but it's not enough. Most often you have to combine this EO data with in situ data. And know that we have very nice EO data. The bottleneck is clearly the in situ data, but the situation is evolving also. We have more now, is maybe this one. So we have the data, we have the cloud, we have the tools, and it means that researchers and users in agriculture can have access not only to Sentinel data, but to basic agriculture products to make their activity. So at the field level, you can get your cropland, your crop type, or your LAI, your NDVI, and you can combine this information already computed with existing meteorological data or models, depending on your application, and you can put your effort in more advanced products. So of course, phenology for agricultural practices monitoring, using phenology to estimate the yields, to estimate the crop production, and so on and so on. And this is something really new. It means that the persons who are doing this kind of advanced research do not have to spend time on generating the LAI. LAI is already there. And the same for the cropland. The cropland is already there. And so you have already this information. And so it means that when you are monitoring the phenology of your field, you are monitoring the phenology not in every pixel of your country, not in every cropland pixel of your country, but you can do your monitoring only for for instance, fields of winter wheat. You can already be crop specific when you are doing your monitoring or your phenological application. And this is really something new, because these products now they exist, they can be produced. Another example that comes from a different project, which is Sen4CAP. So here, this is a project which is targeted the Common Agricultural Policy. So using the Sentinel-1 and Sentinel-2 data to support the monitoring of the agricultural practices in Europe. And maybe just to mention that in Europe, we are lucky because we have what we call the LPIS, so the Land Parcel Identification System. It means that we have for each field the boundaries of these fields which are delineated. And so here we are working not by pixel, but we will be working by object at the field level. And so in Sen4CAP, the idea is to use not only Sentinel-2, but also Sentinel-1. You can see here in green, we have the NDVI, but in red and black, we have the Sentinel-1, the backscatter and the coherence. And you can see that we can monitor the harvest, for instance, of the winter wheat. And the monitoring is so accurate that you can identify the week of the harvest. And after that, you can monitor if here it is a catch crop, but if a catch crop is put in place and is being developed during a certain period, which comes from national regulations in each country. So this is another example of what can be done with these basic products. And the last example, maybe this is not here, this is a bit different, a different project. So this is a project which is funded by the Belgian Science Policy, which is called BELCAM. And here the objective of this project is to provide a platform for the farmer to allow the farmers monitoring their field. And so this also builds on Sentinel data and on LAI and DVI, so all these phenological indices. And this is in near real time that the information is provided for the farmer. And from this information, of course, we do not only provide LAI, but we provide more useful information for the farmers. Farmers are not able to interpret LAI. And so, for instance, what we provide here, this is on the curve. There is this curve that is building along the season, and we, in fact, compare the curve of the field of the farmer with here the average of all the fields with the same crops in its neighboring environment, for instance, in a circle of 3 kilometers. And so the farmer can see along the season how his field is behaving in comparison with the surrounding parcels which have the same crop type. So this is important for the farmer. And another information that is derived and that is also provided really along the season is what we call the NNI, so the nitrogen nutrient index. So this is an indicator, let's say, of the content of the nitrogen in the field. And so here along the season, the farmers can see if his field is saturated or not in nitrogen. And so, for instance, he can decide if he will put the third application of nitrogen at the end of the season. If his field is already saturated, he should not put the third application because it's a loss of money for him, and also it has a negative environmental impact. And okay, all right, that's all for this application. This is really to show that a lot of new possibilities come from these data, these clouds, and these basic tools that allow going one step further in what was currently or most oftenly done before in the field. And thank you. That's all from me.
Thank you so much, Sophie. Very quickly, a question that is related to what you said, the total LII or green LI, Dieter is asking. You were mentioning the LII.
Yeah, this is for the moment, this is really the leaf area index. This is not the area index. I probably need to read the question to be.
Yeah, so.
No, this is the total LAI. This is not the green LAI.
Yeah, okay.
But so I think both of them can implement it. We know this is not the same, but this is, for the moment, this is the LAI.
Okay. So I am thinking we should end in about, 6 minutes. So we will go quickly through the questions. Thank you so much, everyone, for asking. I saw a question about the parcel boundaries. The boundaries were mentioned both during several of the presentations. I don't remember exactly. Well, definitely last for you, Sophie. So Sarah is asking, the parcel boundaries data which you have for Europe, is that open data? If so, what is the source of that data?
So the parcels in Europe, if this is open or not depends on the country. So this is owned by the country. Some countries put it as open data, other countries, and I would say most of the countries do not put them as open data. We get them because we get the data because we are working with the countries. This is really end-to-end project, and so we are demonstrating, testing what we do with them. And so this is why we get the boundaries.
Yeah. So I think another challenge in I think it's I don't remember if it's the Kampala or the Dubrovnik, but we are actually there trying to use artificial intelligence to identify those boundaries. So if you don't have them as open from the government, which is collecting this, you can actually use, or we're about to develop tools to be able to identify those boundaries. So just to comment on that. Yeah.
I would say for some application, you don't need necessarily the boundaries, and it really depends on what you want to do. What I have presented with Sentinel-2 is really by pixel. And when you see the crop type that we get by pixel with Sentinel-2, in most of the countries, we get the boundaries more or less done.
Yeah, but this is, and you mentioned towards the end the ELPIS, and that's also some countries are more reluctant than others to share this information. Yeah. Okay, so let's go. I will start from the beginning with the questions. So, from the early on. Hafiz is asking a very technical question here. Which data, backscatter, coherence, etc., from Sentinel-1 we can compare with optical data? Is there any difference if we compare backscatter versus optical and coherence versus optical?
Maybe I can start with Guido. Cozmin can complement probably much better than I will do. For me, this is not that you have to compare the data. Each backscatter and coherence and optical data can be used. And so you will not look at the same behavior. For instance, if you are looking at the coherence to detect an harvest, you will look at an increase of the coherence. You have to identify which pattern corresponds to the event you want to observe. And you can use as many sources as you want.
Yes. Guido, you want to add something to that?
Yes. I think I agree that in principle the information is complementary. So it's not that what you see in one you automatically see in the other, but you see additional things. So, for instance, coherence is interesting to understand whether there is a crop cover or not. So this is a bit more like a binary information, right? It's like, the coherence basically means, does the structure of the field significantly change between the days of observation? And if you have a crop, that means there is no coherence, because the crop does change, over the period. But if you have a bare plowed field, for instance, or a bare flat field, that will remain actually coherent. And with backscatter coefficients, you get more information on structure. So LAE is related indeed to the leaves and chlorophyll, etc. But backscatter coefficient is more related to whether the crops have big leaves or cereals. Like cereals are vertical. Well, of course, if they start to elongate, right, with the ears, then that has a very distinct effect on the Sentinel-1 SAR, and you see many applications, for instance, in rice, where people use Sentinel-1 for rice production. First of all, because of course there's always clouds in those areas, and but rice has a very distinct behavior in Sentinel-1, and that's why they actually they can easily follow start of the season, end of the season, etc. And that's a bit specific to rice because it has this vertical structure again. But you can apply this kind of knowledge everywhere. So it's also very easy to, for instance, find winter wheat from grassland or this kind of stuff. So the idea is, of course, depending on what problem you are interested in, you should then look at what your sensors will give you in terms of information that is required.
Yeah, and I think, Cozmin, if I'm not mistaken, what we would like to explore here is going deeper into exactly this question, actually, to see if there's any, if it's possible to develop algorithms that combine all these different perspectives on the crop, on the field, and provide some new information that is useful for those who are interested, depending on the use. Is this correct?
Exactly, you are perfectly right, and I fully agree with my previous comments from Sophie and Guido concerning the complementarity of the both kind of data, optical and radar. It's really important to have at the end an operational solution, because with the optical data sometimes it's maybe easier to process and to have an answer, but the problem is that when we don't have this optical data. And it's also important for SER data, as Guido mentioned, this queryance product that can give us very useful information concerning the agricultural practices, harvest, and so on. But yeah, you're right. The idea is to combine all this kind of data to obtain an operational product at the end.
At the end, yes. And just I wanted to clarify something concerning the use of Earth observation. We are talking about Earth observations. We are talking about Copernicus and Sentinels. And Guido, you were talking also about ancillary data. And I just want to repeat the definition of Earth observation in GEO, in the group of Earth observation. It's all types of observations of the Earth, not only the space-based, like the Sentinels are a type of Earth observation, is space-based observations, but you also have field observations, so you have different sensors on ground, so ground truth or in situ, as we call them, and you have also different. You can fly, airplanes. You have different types of distance to what you observe. So all of that information is what we collectively call Earth observations. Oftentimes we talk about Earth observations only as space-based, but that's not. It's the whole package of perspectives. Just to clarify that. And so if you are interested, I saw Akin was asking me, what are we, if you are a young scientist or a scientist to be, you are perfectly welcome to join this group. To solve this, we need different types of background and perspectives. And I think you, Guido, you mentioned this in your presentation, that you really need a lot of different perspectives, and even having ideas and not being able to do this analysis is also something that is worth doing. The advantage for young and more experienced of joining this hackathon is that the report that you will be writing as a result of your work will be published, and you can use this for your on your publication list. So you will be able to use it as a reference of your skills and your activity. So it's beneficial for you in your career. Okay, do we have any more questions? I kind of lost. Sophie, you answered a question here. Did you? Sorry, I lost. So you see in the chat, some questions are answered. Dieter is asking, I'm going to Dieter now. You can actually compare intensity data from Sentinel-1 with optical data, whereby it is obvious that it will not represent the same feature for all crops. We covered this over this whole season. In other words, yellow flowering crops cause a significant drop in NDVI, but not in SAR. There are other issues as well, but you can get a proxy for LAI. Do anyone care to comment on this? It's sort of a comment, but there might be some valuable information that you might add on to this comment by Dieter.
Yeah, I can very quickly answer that. Check the reference that I have in my second last slide. This talks about yellowing, flowering crops, and it actually also causes a drop in SAR. So and that's a publication in recent publication. So, but what is nice is that in optical it is due to the spectral appearance of yellow flowers. And in SAR, it is related to a slight change in the structure of the top of the crop. So different, say, physics, but in a way, okay, coincidentally, the same kind of signal behavior. But that is, of course, cause and effect. But it's really the physics that is important there.
Yes. Okay, Amit is asking, I think this will be the last question before we conclude. Amit, can this tool be used for forest phenology and change assessment? Have you any experience with this?
So we in the lab and in the consortium, we did not use it for forests, but users already use it for forests. In fact, there is no reason that it doesn't work for forest assessment. It's vegetation monitoring. And so this was developed for agriculture, but we know that people are using it for forest also.
Yes. So the main idea, very simply said, is to work on improve the combination possibility to combine these different types of data, optical and radar, to put it very simple, to various applications. And you've learned today that there's been done a lot of work. The data is there available for you, and you will be giving some help to access it. I posted also a link to NextGeo's data catalog. We have a couple of agricultural pilots there who has been using Sentinel data for their applications. So it's possible to find also examples of use of the Sentinel data on agriculture. It's NextGeo's Data Hub. It's a place where you can easily discover the data you're looking for. So that's another option to find your data, to discover the data. We will help the best we can. Cozmin will be the mentor, and we have this very competent support from Sophie and Guido also at your ready to help you if you want to join, which we highly recommend. We thank you so much for the engagement, by the way. Clearly there's a great interest. Don't hesitate to sign up with Cozmin, and Cozmin will tell you what next to do. We among other things, we will map out the different interests and the background you have, so that we can find have an overview of the resources in this challenge, and Cozmin will help out with that. So you will get some assistance and it depends on your background, right? What you will make out of this. What else? If you haven't, this is an all virtual hackathon. So the working mode will be like Cozmin will write you when you register. You will give him your email, so he will contact you. You will have a Skype channel to chat, to discuss questions. You will also be able to meet there whenever necessary. That's Cozmin who will summon you. You will have a Google Doc space where you write what you are doing, propose ideas, etc., where you record your work. And then finally, there will be a presentation at the virtual workshop where all the challenges in the hackathon will be presented. And that will be for Dubrovnik, will be on the 13th of May. And until then, you can work as much as you want with Cozmin and the rest of the teams that has registered. Okay.
Yeah. Bente, just a quick question. How are we going to provide the presentation?
Yes, so please send me the PDF version of your presentation. Okay. We will post, so this webinar is recorded and it will be made available on planforall.eu, so planforall.eu. And together with that recording, we will also have a link to your PDF. So for those of you who wants to check out the PDFs, that's where you can find it. But I'm sure also you can send it also, of course, to Cozmin, who will send it directly to those who have registered for the.
Fine. Okay.
Yeah. Okay. I think we should call it a day now. Thank you so much. Thank you all presenters. Excellent work. And thank you dearly for your willingness to support the participants. This is a really great offer. And Cozmin, I just wish you luck with working with this very active group of people.
Thank you very much, Bente. Thank you very much to Guido, Sophie, and everybody to participating to this this challenge. And I'm waiting for your feedback.
Excellent. Bye-bye.
Bye-bye.
Bye.
Bye.